All right, this is a presentation on deriving the constant acceleration motion equations. If you read chapter 2.5, they go through a derivation of those equations. I'm going to take a slightly different approach based on the graphing that we've been doing in class. And you'll see, you'll know how to do this once you see how to do some simple geometric calculations. That should make sense. So take good notes. All right, so first what we're going to do is we're going to start out by drawing. As you can see, I have some graphs of position, velocity, and time. And I just arbitrarily used x as my position variable. We could have just as easily used y or z. And of course, we're doing constant acceleration. So I'm going to start on the acceleration graph. And let's just draw at an arbitrary level. I'm just going to draw my acceleration a. All right, so there's my constant acceleration graph. And the question is, using that graph, what can I figure out in terms of the other equations that are going to occur as we draw these other graphs, as we move up the scale to the velocity and the position graph? Well, first of all, we can figure out the equation for the first graph of the acceleration versus time. And I'm just going to write it over on the left side of the page. And you'll see later here why I'm using these numbers over the side here. I'm going to put in equation number 7, our acceleration as a function of time is a constant function. So all we have to do for that constant function is to write the value of that level that it's sitting at. And in this case, it's just some level a. And that a could be a positive number, it could be a negative number, but it's just some number a. All right? So that's our first motion equation. That's quite easy to get, is that our acceleration as a function of time just equals a constant. The next thing we do, of course, is we look at these graphs and we work out the next graph above, the velocity versus time, and we use that using areas. So let me switch to a different color here. And what we're going to do is we're going to take a representative area here, and let's work out what that area is. Area of that rectangle equals base times height. Now the base, and I'm going to use some general time units. I'm not going to use seconds here, like 2 seconds, 3 seconds. I'm actually going to use just time. And so the width of this is some time increment. We're going to call it delta t. All right. So the area of this is the base, which is delta t. And the height of this graph is a. All right. So delta t times our height of that graph, height of that location, which is x. So the height of all these rectangles is from the t-axis up to the a line, and it's a constant value. All right, so our area, it turns out, is delta t times a, and of course we know that our area represents our change in our velocity. So our change in our velocity must equal a times delta t. All right, so one note that we want to make up here when we're working on this is that when we talk about delta t, it means take the final time and subtract the initial time from it. And we'll also, you'll see me more likely use t1 minus t0, or t0 is our initial time, t0. But in math class, well, before I go there, our initial time typically in physics, we're lucky because we get to define our initial time, and typically it's when we actually press our stopwatch and start our stopwatch. So typically we set that to 0 seconds. In math class, some future time, we don't use tf or t1, we would just use some future time t. So in math class, this typically delta t turns into just plain old t. All right? So that's a little shorthand saying we're just at some future time, and the difference is starting from 0. So 0 to t, t minus 0 is t. So if we look at this equation then, we can do something similar for delta v. So delta v is our change in our velocity from the graph above. And if I'm going to actually go up to the graph above right now, and let's see. Let's just plot out. Well, we know delta v means it's your initial velocity, final velocity minus your initial velocity. All right. So it's a change. It's a change starting from an initial point, or v naught. So it's vf minus v naught. And basically, we're going to go up in this graph, and we're going to pick out a generic starting point on here. So I'm just going to pick out up here. I'm going to pick out just a random spot. I'll just put it here. Here's our V naught, for example. All right. And for our V naught, what we're going to do to calculate our next point on this graph is we know that we're going to take that amount of area and we're going to add it to the graph above. All right. And in each case, for each time grouping that we're going to use, we're going to have that much area added each time. So it's going to move up by a nice constant rate. So each of these boxes would be a constant step upward in our graph up above. All right. And the size of that step is going to be our A times delta T, is the amount we're going to move up. So let's just say that on this graph, and actually I'm going to move my V naught up a little bit. I'm going to start V naught right here. And so my next point is going to be up at some level A delta V. And I don't have a scale written up here, but what I'm going to do is let's just say A delta V is that much. So from here to here is A delta V, delta T. And then for the next time frame, we get to move up another step of time, A delta T. And then the next time frame, we move up another step, A delta T. Right, so in each case, our step size is A delta T. So we step up at a nice uniform rate. And of course, if we were to connect these points, we actually know that that's going to be a linear progression. And if we were to look at the slope of this, the slope of this progression would be, well, our rise, which is A delta T, over our run, which is just, in these cases, this run is delta T. So our slope is just A. I'm sorry, but my pen here on the smartboard is not acting as nice and neatly as it should. So slope equals A. All right. So I've got the slope of that line is over there. And if we want to come up with the equation for the line, well, we can just use our y equals mx plus b format. So, but of course, instead of y's, we have our velocity in the x direction. And instead of x's, we're going to be using our delta t, or our time. All right. And the question is, what's our slope? We just figured out our slope was A. So we've got, let's neaten this up a bit. We've got acceleration times time. And our y-intercept for this is our initial velocity. We'll call that dx naught. All right. So there's our next equation. That's our equation for velocity as a function of time. And we're going to write that in equation number 6 over here. So our velocity as a function of time equals acceleration times time plus your dx naught. All right. And you'll see later why I'm putting these in number 6 and number 5 and so on and so forth. Another could you guys just block the door open? Another interesting item that we know that we put up on this graph is if we were to look at 2 points on this graph. So here's our V initial, and here's our V final. And if we wanted to know what the average velocity is between these 2 points, we talked about, because this happens to be a straight line, and this is a straight line, it's a linear function because down below we have a constant function. So to find out the average value from our initial velocity to our final velocity, if we picked any 2 points on this line, would be just the midpoint of the line. So we know to get the average velocity, we call it V average or a V bar. Sorry, once again, my pen is not running neatly here. Our V average would equal just the midpoint, using the midpoint formula for our height values. So I take V1 plus V0 over 2. All right, so I can take an initial and a final velocity over 2. And actually, I'm going to write that down. I'm going to call that equation number 10 over here. So my average velocity is v1 plus v0 over 2. All right. So average velocity, well, we learned about that in actually chapter 2.1, and they talked about speed. And let's just go back a little bit in time. Speed, you've known from 5th or 6th grade that speed equals distance over time. All right, and this is distance measured on an odometer, and this quantity gives you your average speed. All right. Of course, then we learned in 2.1 and 2.2, there's another quantity called velocity. And our velocity is not our distance divided by time, but it's actually our displacement, delta x, over our time, t. All right. And once again, the equation we started with back in the day was delta x over delta t. And just remember up top, when we talk about delta t, really our t naught is generally speaking, we set that to 0. And our later t, we could call t final or t1 or just plain old t, some future time. All right. So we have these equations that we know and love and we've already used. And we might as well throw up one other here. In section 2.3, we learned about average acceleration. And the bar across the top of these means average. And average acceleration is just delta v over delta t. Okay, so those are some basic equations that we know and love. But you'll notice I've drawn this big blue line across the board because the equations up here can be used in any instance for any general case. But the equations down below here, these are special equations that can only be used if we have constant acceleration. All right, these are what we call constant acceleration equations. So all these equations that we're driving below this line, all these equations are predicated upon having constant acceleration. So if you don't have constant acceleration, you cannot use these equations. Don't forget that rule. All right. So, all right, we've looked at our velocity graph. We figured out our equation for that straight line that we drew, that linear function, and we've also found the midpoint as the average. So how do we get our position versus time graph? Well, we move up once again using areas. And so we're going to be looking at areas under here. So we'll have, let me use a green pen for areas here. So we're going to look at these different areas, and we look at these shapes. They're trapezoids. All right. I'm just going to draw one of these trapezoids. I'll just replicate it up here. So we've got these trapezoids up here. And the question is, how do I calculate the area of this trapezoid? Because we know the area of this trapezoid is going to give us our change in our position in the graph above. All right. So the question is, how do we do that? All right. Well, there's a simple way to do this. It's probably just to split it into a triangle stacked on top of a rectangle. All right. So let's just take these areas and add them up. All right. So we've got this rectangle has a base that's equal to delta ty. All right. The height of this, if you look down below, let me just rewrite this. It's getting a little bit sloppy. My pen is going crazy. So if you look carefully at the graph down below, we've got the height is actually from here to here. All right, for this side of the curve. And actually that height equals, well, V naught. From 0 up to V naught is V naught units high. All right. The width of these is delta t. On this triangle up here, the width is also delta t. The question is, what's this height right here? Well, that height is actually from here to here. All right. And you notice that height is the amount that we stepped up using the graph below. That's the height we used to step up. And that height was a delta t units high. All right. So this height right here is a delta t units high. So all we need to do to figure out the area to get, which is equivalent to our change in our position, is to actually calculate the area of these two things and add them up. So the area of the square is just the height is v naught and the base of it is delta t. And the area of the triangle is 1/2. The height, the base, 1/2 base height is delta t is the base. That's the base right there. And the height is a times delta t. All right, and we can do a little bit of a simplification here. We got delta t times delta t is delta t squared, so we get 1/2 times a times delta t squared. And if we add these two things together, what do we get? We get, and I'm going to erase some of this down below us here to give some room. We get the area, which is delta x, a change in our position, equals 1/2 a delta t squared. That's for this portion, the triangular piece of this. And the plus this bottom piece, which is just v naught times delta t. All right. Of course, delta x is just, we can re-represent delta x as we did before. Delta x is x final minus x initial, or I more typically use x1 minus x0. All right. And in math class, you wouldn't say x1, you'd probably just say some future value of x. So it's x minus x0. So I'm going to put x minus x0 in for delta x here. So I have x minus x0 x naught equals 1/2 a. And remember, delta t, if our initial time is 0, just turns into t squared plus v naught times t. All right. If I move this x naught over the other side using addition, I'm going to get our result x equals 1/2 ax t squared plus bx naught times time plus our initial position x naught. All right, and you'll notice that that's an equation for a parabola, and that parabola we plotted using that equation, and we get an upward pointing parabola of some type that we could actually graph based on whatever our coefficients of ax, bx naught, and x naught are. If you took your notes out of the book, you should recognize these equations. And actually, I handed out in class a page of notes to you. And you should recognize from this page of notes that I've got equations 1 through 10 on here. The ones above the line are for all types of motion, whether they're uniform acceleration or not. And I just talked about what delta x and delta t mean. And here's your equation number 2 that we already saw on the other page for speed equals distance over time for average speed. Here's average velocity, average acceleration. And here are the equations that we just derived for the top chart over here, the velocity graph and the acceleration graph. It shows us for each one of these what the equation is based on our little derivations we worked out. And we also, along the way, we worked out the equation for average velocity. When we use these equations, the equations below this line can only be used if you have uniform acceleration. And I have a comment to that effect here. So we can only use equations below the line, 5 through 10, if we have uniform acceleration, or if we can make a reasonable assumption that could be a good model for the situation. Any of these equations above the line can be used for any type of motion situation, because they're just using average values.